There's something off about 3I/Atlas. During late July, premier observatories such as Hubble and JWST gathered remarkable observations of this uncommon interstellar comet. Right when its coma expanded beyond 300,000 kilometers and accounts surfaced of a greenish hue along with unusual intensification, the formal announcements suddenly ceased. NASA pointed to solar positioning and protective protocols as the cause. Yet this sharp pause feels conspicuous, especially compared to the quick succession of updates that followed Oumuamua and Borisov. The lack of details isn't merely sparking outlandish speculations. Failing to deliver prompt explanations risks eroding confidence in the transparency of celestial findings. So, what's truly behind the information drought? And what details about 3I/Atlas are being withheld? On July 21, 2025, the Hubble Space Telescope focused on 3I/Atlas, producing the clearest photos to date of this cosmic traveler. 2.5 weeks afterward, on August 7th, those photos became available, revealing a core measuring no more than 5.6 kilometers in width and an extensive dust trail extending toward the Sun. By August 6th, the James Webb Space Telescope stepped in, employing the NIRSpec tool to collect spectral data. However, for JWST, just raw technical summaries and initial remarks made it to the public. Nothing in the way of standout visuals, only suggestions that evaluations were in progress. Gemini South contributed on August 27th, snapping shots that verified the comet's vigor and tail development. That information entered the open database on September 4th and 5th, offering scientists and hobbyist stargazers fresh views of the enlarging coma and altering dust patterns. Every disclosure triggered waves of digital chatter, though the gaps between them began to lengthen. Following September 22nd, the rhythm shifted. No additional key visuals, no updated datasets from Hubble, JWST, or Gemini. The stream of authoritative reports dwindled to nearly nothing. For those following the comet's trajectory, the void was glaringly obvious. What was once a consistent series of public disclosures now featured an expanding silence. The issue extended beyond what had been observed to why no further insights were forthcoming. Monitoring 3I/Atlas via Hubble or JWST involves more than aiming and firing. Each observatory adheres to rigid sun avoidance guidelines, operational constraints designed to shield their vulnerable lenses and sensors from unintended solar glare. Hubble's policy is straightforward: observations prohibited within 50 degrees of the Sun. JWST, equipped with its enormous sun shield and fragile infrared detectors, imposes an even tougher standard of at least 85 degrees separation. These restrictions are non-negotiable, embedded deeply in the operations. Should an object approach too near the Sun's sky location, the programming prevents any booking or performance of sessions. The dangers go beyond hypotheticals. Unfiltered sunlight might fry the equipment, irreparably harm sensors, or jeopardize the whole project. As 3I/Atlas advanced on its route, the solar elongation, the angular distance among the comet, our planet, and the Sun, narrowed progressively. In late August, it exceeded Hubble's 50 degrees boundary. Shortly after JWST's NIRSpec session on August 6th, the comet breached JWST's 85 degrees limit. From then on, both facilities faced a mandatory shutdown. The experts at the Space Telescope Science Institute, responsible for timetables and functions, simply had to pause activities. The exclusion areas are programmed directly into the planning software. Efforts to circumvent them would activate emergency safeguards, potentially suspending all research until a thorough investigation. This stems not from excessive red tape, but from unyielding physical realities. Even pressing alerts for immediate targets can't skirt these barriers. The sole remedy is patience until the alignment shifts. For 3I/Atlas, that translates to no fresh premiere photos or readings until its elongation widens once more, according to trajectory models, scheduled for early December. In the meantime, the moratorium persists, leaving the leading telescopes quiet, not from preference, but necessity. Clues regarding 3I/Atlas's essential makeup started emerging with the initial scientific outputs. Hubble's July shots displayed not only a dust stream, but a vast coma. a gaseous and dusty sheath spanning almost 348,000 kilometers. That's over a quarter of the Sun's width and substantially bigger than typical comets at such a range. The most captivating aspect arose from preliminary spectral observations. Researchers began murmuring about an exceptionally prominent carbon dioxide signature in the coma. To clarify, as of late September, no formal, vetted quantitative analysis has verified carbon dioxide as predominant, yet the indications persist, and the research groups haven't refuted them. For an interstellar body venturing into the inner solar system initially, this would signal a significant compositional insight. Conventional solar system comets tend to be water-led at this proximity. In tandem with professional outputs, backyard skywatchers match the effort through their personal viewings. A number noted a clear verdant shade in the coma, probably due to dicarbon or psi-carbon-based compounds. The hallmark indicators in comet atmospheres appeared here with a distinctive flare. Certain watchers pointed out that the greenish hue was more vivid and enduring than what's usual for these celestial wanderers. Lacking comprehensive spectral analysis, though, it's tough to nail down the reason behind it. The sunward jet, initially spotted by Hubble and later by Gemini, grabbed plenty of attention too. Its form and intensity varied noticeably from one evening to the next, fueling arguments over whether eruptions from the surface or angles of observation were responsible. Brightness readings from photometry introduced further uncertainty. Data from hobbyists and experts alike showed big spreads, occasionally varying by over 1 magnitude. Factors like gear differences and setup adjustments explain some of it, yet actual quick shifts in the surrounding dust cloud or core might account for the rest. As major telescopes took a break, these inconsistent earthbound accounts served as the primary glimpse into 3I/Atlas's behavior. Currently, the solidest details suggest a comet boasting an unusually large envelope of gas and dust, maybe loaded with carbon dioxide, featuring that sunward jet, and sporting hues that won't stay consistent. Without fresh input from top-tier instruments, every quirk sparks guesses and highlights our dependence on sporadic contributions from backyard stargazers and terrestrial setups. Come late September, the quiet surrounding 3I/Atlas went beyond mere mechanics. It grew to feel like a personal slight for those tracking it from below. Online forums buzzed with annoyance and theories. One hobbyist stargazer posted, "Feels like pursuing a phantom. Night after night, we're just hazarding shots in the dark about what's going on up there." Someone else wondered, why hold back the unprocessed files? What's the holdup? In reality, the journey from scope to open access isn't speedy. Captures from Hubble or JWST land in a holding pattern. After beaming down, they undergo tweaks for accuracy, zapping of space radiation glitches, fixes for sensor oddities, and stripping of stray light. JWST's workflow amps up the complexity. Every near-infrared readout cycles through various digital filters, with specialists scanning for flaws or tuning mistakes. Overlooking one phase could lead to spotting a molecular trace that's bogus. On top of the tech challenges, rules come into play. Hubble and JWST both enforce exclusive access times, typically half a year for Hubble runs, stretching to 12 months for JWST ones. Lead researchers and their crews claim initial dibs, a custom designed to honor those who crafted and secured the observation slots. Though a few opt to share sooner, most hold off until their groups have pored over and verified each detail. That's doubly so for spotlight cases like 3I/Atlas, where jumping the gun might stir up waves in research circles and news outlets. Organizational steps pile on more. Any announcement or key photo routes through bodies like NASA, ESA, and occasionally CSA for JWST. Teams vet the info, probe for legal snags or pact breaches, and sync release dates. Even straightforward data sets can linger for weeks in this approval chain, pending nods from science heads and PR folks. For 3I/Atlas, things dragged as groups mulled the dangers of dropping half-baked or unclear findings. As a JWST team member noted, better to nail it eventually than botch it in a rush. Interstellar objects don't offer do-overs. This setup ensures that while everyday enthusiasts and volunteer experts crave news, the formal paths proceed deliberately. That lingering anticipation, poring over recycled visuals amid buzzing chatter, is woven into the framework. To much of the crowd, the gap acts like a barrier. To planners and processors, it's a safeguard for precision over cover-up. Yet as the hush drags on, it molds discussions, morphing standard holdups into sparks for wild ideas and everyday prudence into brewing doubt. Whispers about 3i/Atlas snowballed right after the big scopes hushed up. Some online chats blamed secret gear, positing that defense or spy craft had grabbed shots forever hidden from view. Different voices pushed the notion of curbing alarm, theorizing that officials were scripting the narrative, withholding info to dodge scary buzz about an otherworldly oddball. There's a faction insisting the findings are just too bizarre for swift unveiling, that experts are hustling in private to decode what defies standard scripts. The news ecosystem stokes the fire. Tales of flashy comets like C/2020 F3, Neowise, or C/2021 A1, Leonard, vivid, approachable, and camera-ready, dominate feeds and front pages. Their appeal turns them into click magnets. Stuff visible right now always racks up views. Meanwhile, 3i/Atlas, hampered by spotty news and obstacles, slips off the hot topics. In the void of fresh visuals, conjecture rushes in. After the release of images from Gemini South in early September triggered a massive surge in social media buzz for 3/Atlas, reaching engagement levels tenfold above the norm for ordinary comets, before shifting into conspiracy-laden tags as the information void widened. Yet, the actual workings behind the curtain prove far less sensational and much more systematic. Observations captured by Hubble or JWST undergo a rigorous, multi-phase workflow before external researchers gain access. Initially, the unprocessed data get transmitted earthward and annotated with satellite metrics. Calibration procedures then activate, eliminating cosmic ray interference, fixing sensor irregularities, and deducting ambient noise. In JWST's case, this involves navigating no fewer than 3 primary phases: sensor-specific adjustments, device-specific tuning, and sophisticated handling such as image stacking and flaw elimination. Every phase gets scrutinized for inaccuracies, marked for oddities, and occasionally repeated if discrepancies arise. When the dataset achieves scientific usability, lead researchers examine it, typically during an exclusive review window, 6 months for Hubble, extending to a full year for JWST. Only once the lead team feels assured of the findings does it advance to the subsequent checkpoint: institutional evaluation. Input comes from NASA, ESA, and occasionally CSA, assessing compliance with legal, agreement-based, and research standards. Release coordinators synchronize announcement schedules, at times delaying by weeks until all parties approve. Should the information appear unclear or suggest unforeseen elements, the timeline extends considerably more. A hasty announcement, particularly for a prominent object like 3/Atlas, could lead to embarrassing revisions or outright withdrawals. This differs markedly from past interstellar objects. Oumuamua's 2017 detection unleashed data streams nearly instantaneously, with preliminary papers, lively discussions, and rampant theories flooding online in mere days. Borisov, arriving 2 years afterward, adhered to a predictable, by-the-book rhythm, with photos and spectral analyses shared promptly and without much fuss for 3i/loss. The interplay of engineering challenges, deliberate scrutiny, and cross-agency approvals has fostered a halting, irregular progression. Consequently, this setup brews an ideal environment for gossip and impatience. Still, amid the clamor, the system advances methodically, phase by phase, each designed to intercept errors prior to public exposure. For those technicians and data specialists immersed in it, the emphasis isn't on concealment or narrative management. It's on ensuring scientific accuracy, regardless of the extended delays it imposes. The upcoming Mars encounter on October 3rd offers the prime chance for fresh insights into 31i/Atlas. During its nearest approach, the comet will skim within 0.19 astronomical units of Mars, roughly 28 million kilometers away. That's relatively near on astronomical scales, yet still too distant for detailed imaging. The ExoMars Trace Gas Orbiter, or TGO, hosts the CASSIS instrument, renowned for its crisp 5 meter per pixel views of Mars terrain. However, at such a range, CASIS encounters strict optical constraints. In the optimal setup, a single pixel spans over 300 kilometers. Thus, the core of 3D Eye/Atlas, measuring anywhere from 320 meters to 5.6 kilometers wide, would appear merely as an indistinct speck. No contours, no form, simply a dim glow amid the stellar field. The HiRISE tool aboard Mars Reconnaissance Orbiter, benefiting from a bigger mirror, manages slightly finer resolution, around 34 kilometers per pixel, but that's vastly insufficient to resolve the core or features in the surrounding dust cloud or trail. These instruments were engineered for detailed planetary surveys up close, not for pursuing distant wanderers streaking through space. Following a fast-moving comet at interplanetary velocities falls outside their standard operations. Shutter durations must remain brief to prevent blurring, and the clarity of the signal deteriorates quickly as the object dims farther out. So what practical contributions can these Mars satellites provide? Brightness assessments, capturing the comet's luminosity at a time when ground observatories and major space telescopes face obstructions from solar positioning. Spotting it as a point source from Martian orbit aids in monitoring its trajectory and behavior, particularly if an abrupt flare or luminosity shift occurs amid the pass. Data handling is swift. TGO and Mars Express can relay and refine these captures in just 1 or 2 days, assuming no glitches. Yet for those hoping for vivid proximate shots, it's wise to temper hopes early. The Mars transit prioritizes opportunistic observation over fine-grained visuals. Its true worth emerges in filling an observational blind spot when all other vantage points must avert their gaze. The comet's closest solar approach, or perihelion, for 3 Eye/Atlas falls on October 29th or 30th, with it arcing to within about 1.36 astronomical units of the Sun. At that separation, it avoids being a dramatic solar skimmer, though the intense warming and swift motion still impose significant strain on its core. Therefore, as 3 Eye/Atlas navigates this solar phase and returns to view in December, what key indicators merit attention? Start with the brightness profile. Abrupt surges, particularly brief and intense peaks, might indicate crustal breakup or sudden ejections. A gradual increase and decrease, aligning with projections as it approaches and departs from the Sun, would align with anticipated patterns. The solar direction suggests a consistent outgassing process instead of disintegration. Keep in mind that one isolated surge in luminosity doesn't indicate breakup. It's essential to observe a consistent trend, preferably verified by several independent viewers. Afterward, examine variations in the anti-tail, that sun-facing extension visible in broadview photographs. As our planet's location moves compared to the comet's path around the Sun, this feature might twist or weaken. Regarding 3 Eye/Atlas, the anti-tail's visibility ought to reach its height near perihelion, then quickly fade as the alignment shifts through December. Monitoring its direction in various shots provides a strong method for validating trajectory information and particle dynamics. Color plays a role as well. Should the green shade noted by hobbyists vanish or alter post-perihelion, it might signal the depletion of specific compounds when ices on the surface dwindle or new substances emerge. Yet, only detailed spectral analysis can verify the actual shifts. Visuals by themselves might deceive. Come December, with the comet's angular distance from the Sun growing and premier observatories resuming operations, anticipate fresh rounds of detailed pictures and chemical breakdowns. Glancing toward 2026, an advantageous alignment with Jupiter might provide yet another chance for examination if 3 Eye/Atlas endures its close solar brush. At present, the most effective approach involves a skeptical perspective. Contrast photographs from different times, validate brightness measurements against each other, scrutinize bold claims, and recall that hues alone don't reveal composition absent spectral data. Astronomers worldwide, ranging from experts to amateur stargazers, are observing as one. The narrative continues unfolding. It's merely poised to reveal the following chapter. Regulatory reports highlight operational restrictions. The 50 degrees solar keep-out zone for Hubble and 85 degrees for JWST, combined with extended processing timelines spanning weeks and rigid data embargo periods. Even with such justifications, the lack of immediate insights into this interstellar visitor, featuring a coma rich in carbon dioxide, a sunward jet, and mentions of a verdant glow, has kept key research puzzles unresolved. No published, vetted spectral readings detail the coma's makeup, and the scattered light pattern's broader effects stay unexplored. While Mars spacecraft gear up for a near flyby at 0.19 astronomical units, upcoming visuals and analyses, delayed by 24 to 48-hour transmissions, may at last ease the data flow jam. For the moment, the 3I/Atlas scenario illustrates how procedural prudence and equipment hurdles influence global perceptions of these exceptional solar system intruders. What gets revealed and what remains concealed.